Hey everyone, this is Unit 7, Lesson 2. We're going to look at logarithmic functions today and how to go back and forth between an exponential function and a log function and how those are related. So just recall that logs are one-to-one. Like, what makes a one-to-one function? First, it has to pass the HLT. Okay, so if you think about your exponential functions, they curve up this way. So that passes your horizontal line test. So exponential functions have an inverse. And that inverse is what we call a logarithmic function. And so we can find that inverse. Just like before, we're going to change this f of x statement to y equals 2 to the x. And then we're going to switch around the x and the y. Well, now to get y back by itself so that we can graph it, we don't have anywhere to go. So we can't divide by 2, we can't divide by x. So what we're going to look at this lesson is how to convert that into what's called a log or a logarithmic function. And so this actually becomes log base 2 of x is equal to y. So we would write our inverse function as f to the negative 1 of x is equal to log base 2 of x. So we're going to look at today this process here and how to go from one to the other and what that means. Okay. So it's a logarithmic function. We're going to just say log function, and on your calculator it will be the log button. And then just note how to read this. So this is log base a of x when you're reading that out loud. So we have log base a, put them in a different color there, of x equals y. Back in blue. And we can convert that to an exponential function. So this goes both ways. We'll be able to convert, if you remember, biconditional statements from geometry, but it works both ways. And the base of your log is always the base of your exponent. So we're just going to kind of loop around here. So a log is always equal to an exponent. And so that y becomes your exponent value. And so we have a to the y. This is a really bad y. A to the y is equal to x. Okay, so you'll always be able to convert from a log to an exponential or from an exponential back to a log. So logs are really just a rewritten exponent. Okay, so the form works both ways. The inverse of an exponential function is a log function, and vice versa. So again, we can go either direction with this. Log base a of x is y, right? So a to the y power is x. All right, so just always keep in mind that a log is equal to an exponent. special cases for logs. There's a couple different ones that we'll look at. Your common base for logs is base 10, so it's kind of like our square root. It's the most common root used, so we don't put the little 2. You will, if you have a base of 10, you'll just see log. So anytime it just says the word log, it's a base of 10. If it's a base of e, which remember is the number 2.71 and so on and so forth, then we will write ln. So you'll find a calculator button that says ln. That's what that's talking about. It's a base of e. All right, so just practice moving back and forth from one to the other. Again, if I have log base 7 of y is equal to z, I'm going to start with my base. A log is equal to my exponent, so I'm going to make it equal to what I'm taking the log of. So 7, sorry, let me back up here. Just realized I wrote that wrong. Log base 7 of y equals z. Let's try that. So starting over. 7 to the z power, goodness gracious, I can't write tonight, is equal to y. So again, always just starting with your base value, exponent, what it's equal to. Going the other way, if we have 10 to the 5th is equal to x, that means log base 10 of x is equal to 5. Okay, so moving back and forth between the two. Eventually, the goal is to be able to use equations, convert back and forth, and solve for variables in different positions. So go ahead and fill these boxes in. Pause the video for a second and try it yourself. Okay, there you go. Just refer to above as to how I swooped those around. All right, so 10 to the 3rd is 1,000, and so on and so forth. Okay. All right, some more for you to try. I just want to point out real quick, ones like this, same thing. If you don't have a base, remember that your base is 10. If you're dealing with natural logs, you have a base of e. But other than that, we're going to treat this the same way. So we have 10 to the 75th is equal to 2a plus 5. We could then move on from there and solve for a if we wanted to. But go ahead and try some of these. Pause your video again and get those put in. Okay, go ahead and check your answers against mine. See if you have any differences. A couple things I'd like to point out is, first of all, that's a 10. But log base 10 is your common log. And you don't need to put the 10. So this would actually read as log of y minus 1 is equal to x plus 6. Log base e is your natural log. See the previous page for this. And so we wouldn't put log base e, we would write that as ln, as in down here. So the natural log of x is equal to negative 2. Okay, so just pay attention to those things. Same thing up here. I should have changed this here. This would just be log of x equals 5. Okay. A couple special properties of logs as you're going through, helpful things to remember um, in terms of the base and what you're taking the log of. Um, you think about, again, a log is always equal to an exponent. So if we're raising a to a power and it's always equal to 1, well, that power then has to be 0. So a to the 0 power is equal to 1. So if you have log base of anything of 1, it should equal 0. Same thing here. Think about what this would mean in terms of we're taking the log of something, so it equals the exponent. So if I'm raising something to a power and I'm getting back out that same value, well, I'm raising it to the 1, right? A to the 1 equals A. That's the only way to get something back out of itself, is if I'm just raising it to the 1. Well, that being said, if log base A of A is 1, if I raise it to an exponent power, it's just going to equal that exponent. So one way to think of this is we're going to take x times log base A of A. Well, this is just going to go to 1. And so x times 1 is x. And we'll see that a little bit with some of our other rules. But same idea here. We're raising a to a power here to get a to another power. Well, then that power needs to match. So another way to think of this is I have a to some power is equal to a to the x. If I'm swooping that around, well, these two exponents have to be the same. And then the last one is if I have a full log in the exponent position. If we think about what that means in terms of converting it, I would have, let's throw a y here again, log base A of y is equal to log base A of x. Well, if I'm taking the log base of two numbers and I'm telling you they're equal, then those two numbers have to be equal. That's just basic exponent rules. So these essentially cancel each other out, and my answer is, again, just x. Okay, so always think in terms of how would this look if I converted it. If we say this is equal to x, then I have a to the x power is equal to 1. Well, that x has to be 0. Right here I have a to the x power is equal to a, so that x has to be 1. Okay? A to the x power is equal to a to the y, or something like that. So those have to be equal. So just think logically, remember your exponent rules, and remember what a log means. A log is an exponent. So a lot of those properties and those rules are still the same. Okay, evaluating expressions. So there's a couple ways you can do this. You can do it in your graphing calculator sometimes, but you can also do a little bit of it by hand, especially if you have a graphing calculator that doesn't allow you to change the base, and not all of them will. So let me pull one up here. I did have second thoughts. I'm going to do this by hand because you do have a non-calculator portion of this exam, and I want to make sure that you know how to do this. So if I have log base 3 of 1, we're going to use those log properties and first convert this. So let's set this equal to x. So that means that 3 to the x is equal to 1. Well, if you look back at your log properties, that means that x has to be 0. A set of 0. There, same thing here. So I have log base 31 of 31 to the 4th. This is just a log property, so we know that this equals 4. But another way to think of it is that if I set this equal to x, then 31 to the x is equal to 31 to the fourth. And so x is equal to 4. If the bases are the same, the exponents have to be the same. Right? And we can just keep using those properties, taking this logarithm and setting it equal to x, and manipulating it in such a way that we can clearly see, again, same bases, then the exponents must match, so x is equal to 1. Seeing logically what that value has to be. There's no other option here. So a couple more times, if I have 10 raised to the log 5, and I manipulate that, or I set that equal to x, then log base 10 of x is equal to log of 5. Well, these bases are the same. There's no base over here, which means it's a 10, which means that x is 5. Should be putting these all in braces here. Bad habit. So eventually, the idea is that you can get to a problem like this and just be like, oh, well, that's going to cancel, and x is equal to the square root of 17, right, using those properties. But if not, you should then be able to manipulate it so that you can simplify it. So the natural log of y is equal to the natural log of 150. I don't know why I used y instead of x, but it doesn't matter. Y would be 150. Okay, so solving those expressions. So go ahead, I'm going to pause the video again, go ahead and see if you can do these. Hopefully you looked and saw that these are a little bit different because now we don't have the same base. There's no rule that applies. So your goal then is to get this base to match if possible. So for example, this one here, 3 to the x, well, 81 is 3 to the fourth. So again, I have x equals 4. I have 10 to the x if I'm converting this. Well, 10,000 is 10 to the fourth. So x equals 4. Right? Doing this again, I have 64 to the x power is equal to 4. Right? So this one's a little bit different, where I need to change this side. So this is 4 to the third raised to the x is 4 to the 1. So now I have like bases, which means that once again, my exponents must match. So 3x is equal to 1, and x equals 1/3. So think about what this means. Power over index, that rule comes back. The cubed root of 64 is 4. Go ahead and try these last two on your own. Okay, here's the answers to those next two. Keep in mind what it means to flip a value and what that means in terms of the sign on the exponent. All right, so these are already set equal to x for us. So we're going to use that in our properties of logs, to solve for this. So we're just converting. So we have 3 to the x equals 243. Right? We want to get this, we try to rewrite this so that they have the same base if possible. So 243 we need to see how many 3's go in, so I'm going to factor this down. Okay, so I have 5 3's, so 3 to the x equals 3 to the 5th, so x equals 5. Here, 3 to the 3rd is equal to x, so x equals 27. Right, and then go ahead and try this last one on your own. Okay, so keep in mind, power to power we multiply, so to get rid of a fraction, I multiply by its reciprocal. So I raise both powers to the second, and x is 36. Okay, the last thing we're going to look at today is the log function. So we looked at an exponential function yesterday. Remember, those look like this. And a log function is its direct inverse of that. So it's going the other way. Should reflect over that y equals x line and be the inverse of it. Okay, that being said, all of the x and y properties that we looked at today in class will flip. Okay, so like today our domain was all real numbers and our range was from 0 to infinity for a parent function. Before transformations, that's going to flip around. So you think about, we have literally flipped our x's and our y's, so why wouldn't our x and y values flip here? So the domain is from 0 to infinity. The range is from negative infinity to positive infinity, or all real numbers. Also, instead of a horizontal asymptote, we now have a vertical asymptote right here at the y-axis, which means that our vertical asymptote is x equals 0 instead of y equals 0. Our x-intercept instead of our y-intercept has flipped. So the x-intercept is 1, 0. So right here, this point here. The function is increasing for b is greater than 1 and decreasing between 0 and 1. That has not changed. So just keeping all that in mind, one thing to note, don't trust your calculator. Because it rounds everything. And so if you look in your table, it will round to a specific value and make it look like it's reaching it. It's not. It also might look like the graph stops. It's not. It's going to keep going and going and going forever and ever and ever. It's just never going to quite reach that line. So that is something that you will have to understand, that your graphing calculator may not be 100% accurate on. So just keep that in mind. Transformations are going to be similar to the transformations that we have always had. So your parent function Okay, so your parent function changes depending on what your base is. So the parent function in this particular case is log base 3 of x. So we're looking at how that is affected by your graphing. So think about what that means in terms of an exponential. So this would be like 3 to the y is equal to x. So generally, your input is your x values, but it's a much easier in this particular case to plug in our y values. So if you think about it, that would be like 0, 1. 3 to the 1 would be 3. 3 to the 2 will be 9. After that, it starts getting a little bit too big to mess with on a graph. So we're looking at then how these transformations will occur. So we still have our ages in our case. The shifts are going to be similar. Let's actually change this to a -2, -2. Give us some differences here. And think about like what that would look like on a graph. So for this first one, you have 0, 1, 1, 3. Oh, I plotted that like I had X's and Y's here. Sorry about that. Jeez Louise. Okay. We have 1, 0, 3, 1, 9, 2, 5, 6, 7, 2. So this is going to kind of curve down like this. It's going to get closer and closer to that 0, but never quite reach it, remember. There's nothing that, no y value that would ever make this 0. So there's no x value, then that is 0. And so when we're talking about our shifts here for number 1, this is going to go right 3, strike that, left 3, because it's in parentheses. And so it's that opposite shift. So all of these points are just going to go 1, 2, 3 this way. This one would go 3 this way. This one will go 1, 2, 3 this way. And so I have this line going this direction. And so it affects my domain, but not my range. So here I have a domain of that 0 to infinity for my parent function, and my range of negative infinity to positive infinity, or all real numbers. And I have a vertical asymptote of x equals 0. Well, over here I've shifted left 3. Well, that's going to then shift my domain left 3. So my domain goes from 0 to negative 3 to infinity. It does not affect my range. That's still all real numbers, but my vertical asymptote is going to be that first value in my domain, excuse me. So x equals negative 3. I'm looking at a vertical line going through there. Okay. And then the second one, I have right 2 and then down 2. So each of these points will go right 1, 2, down 1, 2. So that one will move there. This one, right 1, 2, down 1, 2. This one, right 1, 2, down 1, 2. So something like this. So again, knowing to draw those arrows that it's going to keep going. This affects my domain again, but also not my range. So all of your shifts should affect your domain value for these particular types of graphs. My domain went right and down. The down doesn't matter because I have arrows going both up and down, so that's my range. But it goes to the right 2, so I'm going to have an asymptote at 2, and my domain will start at 2. So vertical asymptote, x equals 2. Range is still all real numbers. I'll just write it that way for now. Okay, so ultimately the goal is to be able to graph these with no graphing calculator. Think about what that parent function is and what those shifts are, and that should be relatively easy. But that's it for now. Get these notes down, and I'll see you in class tomorrow.